Okay, today we're going to take a look at Chapter 2 over geometric reasoning. We're going to take a look at the first section over 2.1, which is called Using Inductive Reasoning to Make Conjectures. Our goal is to use inductive reasoning to identify patterns and make conjecture, and then find counterexamples to disprove conjecture. So when we're using inductive reasoning, a lot of times we are looking for patterns, and here we have three different examples that are involving patterns. So this first one, we start with Monday, Wednesday, and Friday. What's the next one in the pattern? I'm going to give you a minute to take a look at these once we're done talking about them, and I want to see if you can come up with the next few items here. 3, 6, 9, 12, 15. What's the next item in the pattern? And then we got this situation. What's the next thing in the pattern? So I'm going to give you about a minute to take a look at each of these and try to find some kind of example. We can go ahead and pause the video and see what you come up with. Okay, hopefully you've paused and then now we are resuming the video. This example, hopefully you came up with the next sequence, which is going to be probably Sunday. So if we were to look at this as if it is every other day, the day that follows Friday is Saturday, and the day after that would be Sunday. So that would be the every other day. Now you could have chosen other options here. It just kind of depends on what your reasoning is. If you had chosen Monday by going with just the weekdays as opposed to the weekend days, I suppose that could have been a good and reasonable conjecture. For this one, the conjecture should be a little bit more straightforward. As you're counting by threes, the next one should be 18. And then this looks like we're going to the left, then up and to the left, then up, followed by up and to the right. Okay? So those are our conjectures. We think these things are going to happen next. So when we're talking about inductive reasoning, this is really the process of reasoning that a rule or statement is true because specific cases are true. So you make a conjecture, which is just a statement that you believe is true based on the inductive reasoning process. These are things that you observe based on patterns that you notice. So if you sit around looking at stuff and watching various occurrences, you might notice some things. Now, conjectures aren't necessarily true or false. They're just something you aim to prove or disprove. You might notice something and make a conjecture about it, but you might be completely off. That's okay. We just want to make a statement based on your patterns. All right, so the things that you're really aiming to do here are seeing something, observing, and then what do you notice? Okay, maybe it's true all the time, maybe it's not. Maybe there's something completely different that is something that you just hadn't thought of yet. That's also a conjecture that could be made out of this occurrence. So let's take a look at this one. The product of an even number and an odd number is what? I'm going to give you about 10 seconds to try to come up with what you think is going to be the accurate conjecture here, and we can see what we can come up with. All right, hopefully your two options here are either even or odd. But if you take any even number and you multiply it by an odd number, you should find that you always come up with another even number. And we could prove this if we want to verify that we're true. So 2 times 3, that's 6. 7 times 4, that's 28. Even and odd number, when we multiply them together, we always get an even number. If you had decided to put odd here, show me a case where that's actually true. For example, 5 times 5. Well, wait, what's wrong with that? Yeah, that's right. These are both odd numbers. One of them has to be an even number. So until you can find an example that's going to verify that this is not even, we are going to go with the answer that it is even for our conjecture. Alright, so this next example is dealing with the number of segments created by how many collinear points we have on a line. So this first example, we have 2 points on this line. How many segments do we have in between these points? Should see 1 here, should see 2, 3, and 4. Now the number of segments formed by this many collinear points, or n collinear points, where n could be really any number, is what? What's the relationship between these, so n, and these? If you'd like, take a moment and discuss with your group, or whoever you're working with, or take about 10 seconds and pause the video and try to come up with what you think is actually that relationship. Okay, so if we look at this one, 5 compared to 4, 4 is 1 less than what we started with for number of points. 3 is also 1 less than the number of points, 2 is 1 less than the number of points, and so on. So since we're talking about 1 less, we're going to be subtracting 1 from the number of points. N minus 1 would be the conjecture that we make based on this example. Alright, this one is dealing with the picture, and it gives a nice set of data points, and we're talking about whales. So we're learning about migration behavior of California gray whales. Biologists observed that whales go along 2 routes. For 7 days, they counted the number of whales seen along each route. Make a conjecture based on the data. Okay, so we've got this route that seems like it is the more direct route. It bypasses this extra long bay area. So as we follow the direct route, we see this many whales each day. And then as we follow this blue route that goes through the bay, we call it the shore route, we notice this many whales. You can come up with your own conjecture on this one, and there are actually plenty of conjectures you can make about this. The real one, well, it's kind of arguable. As long as you can back up your conjecture here, we can accept it. So the one that I would think would be one of the more obvious ones is that whales tend to want to travel along the shore when they migrate, because we can see that with the increasing amount of whales every day compared to the direct route where there's much fewer whales. But if you find something else, that as long as you can back it up, it'll be acceptable. Alright, so again, remember the conjectures aren't necessarily true or false. There's something we aim to prove or disprove. Even in that whale question, we could disprove whether or not whales like to travel along the shore if we found some more data points, or if we were to find some other information that might tell us something about why what we saw was actually happening there. So to prove a conjecture is true, you have to show it's true for every single case. That can be tedious at times, but we'll try to work through how to deal with that. Now, to prove if a conjecture is false, you only have to produce one counterexample. Find one example that's not true. So our goal here is to look for a pattern, make a conjecture, and then prove the conjecture or find a counterexample. One or the other. If you find one counterexample, great. You're done. If you want to try to prove that it's true, make sure you go through and prove for every single case that it's actually going to happen. Alright, so here's a mathematical example. For all positive numbers here, n, 1 divided by n is less than or equal to n. Alright, so let's just figure out if this conjecture here is true or false. Now up here it says show that it's false by finding a counterexample. So most likely it is going to end up being false. But let's see what we can plug in. Most students would end up plugging in 1 just to see if this is actually going to work out. And this simplifies to 1, which is equal to 1. So that is going to prove this to be true for now. But remember, if it's true, it has to be true for every single case. So let's pick some more numbers, like 2. Alright, is 1/2 less than or equal to 2? I hope you're saying yes. So that's also true. All right. If we were to keep on going higher and higher and higher, this number here, this fraction is just going to get smaller and smaller, and this number is going to get larger and larger. So that's probably not going to help us find the counterexample. So instead of going up in values, let's go down in values. But remember, we're dealing with positive numbers. So we can't go to any negatives. If we try 1 over 0, well, this kind of creates some problems because we can't actually divide by 0, so we're going to have to discount this case for now. But what other numbers are between 1 and 0? What's smaller than 1? Oh, it's those oh so fun fractions. 1 over a half. Is that less than or equal to a half? Well, when you divide 1 by 1/2, we end up getting 2. Is 2 less than or equal to a half? No, it's not. Since it's false, this is our counterexample, where n was equal to our chosen number of 1/2. Now you can find any number of counterexamples. You could use 1/3, 1/4, really any fraction that is between 0 and 1 would give you a counterexample. All right, another mathematical example here. Let's prove this one's false by picking some values of x. I'm going to let you guys take a moment and try to find a good counterexample here. Go ahead and pause the video, and when you're ready, you can go ahead and restart that video and see what we come up with. All right, so again, if we were to try 1 squared is not greater than or equal to 1. It's going to be equal to it. If you try 2 squared is greater than or equal to 1. So that one's going to be true as well. Once again, let's try to go the other direction. Let's try 1/2. 1/2 squared is greater than or equal to 1/2. Well, 1/2 squared is going to give you 1/4. 1/4 is not greater than 1/2. So again, x equaling 1/2 would be a good counterexample. There are many others, and for this case, since we said any real number, what if we tried a negative? -1 squared, is that greater than or equal to -1? -1 squared is 1, and we get 1 is greater than -1. So that would actually still prove it to be true. So it looks like we're going to have to still go with those fractions. So 1/2 would be our counterexample again. All right, here's another statement. Supplementary angles are adjacent. Okay, well, prove it to me that it's false. Find a counterexample. Again, I'll give you a minute to pause the video and try to find an example of two supplementary angles that are not necessarily adjacent. All right, so let's take a look. Let's see, here's an angle. There's another angle, and we can just connect those lines. Let's picture those are connected there. If we make this one 60 degrees and 120 degrees. And of course with angles we should probably give them some names. So like A, B, C, D, E, F. What if we were to take angle ABC and add to it angle DEF? What do we get? We should get 180 degrees. And because we get 180 degrees, these two angles are supplementary. Are they right next to each other, though? There's this big gap in the middle. So that means that they're not going to be adjacent. And these two angles, this picture here, would be a counterexample proving to us that this is not necessarily going to be true. All right, so that wraps it up for about today. So what I'd like you guys to do is work on this for classwork. There's one extra question here. I'd like you to make a conjecture about anything in your life, something that you noticed, something that you sit around and you said, you know, I noticed this about something happening. Perhaps you like to sit in the park and watch dogs walk by, and perhaps you see every dog is a purple dog. Okay, now don't go that drastic. Make sure it's something that actually happens in your life. Include that as well as the worksheet that you can also find on Blackboard that will be available for you for your homework. Reminder of a few upcoming events. Next week we have the Chapter 1 review day and then Chapter 1 test, followed by Friday is a blended learning day on Blackboard, so you'll probably see another video like this one for that class. All right, thank you guys for being here, and I will see you when you come back. Thank you. Bye.